Today's webinar will be presented by one of the paper's authors, Shubh Gupta. Shubh is a PhD candidate in the Department of Electrical Engineering at Stanford University, working as a graduate research assistant under Professor Grace X. Gao. Shubh did his MS from Stanford University in Electrical Engineering in 2021 and his BTech from Indian Institute of Technology, Kanpur, in Electrical Engineering with a minor in Computer Science in 2018. We greatly appreciate the time and work that he's put into preparing for the webinar today. Following the presentation, we will take questions. To ask a question, you can click on the Q&A box in your viewer, and we'll address those at the end of his presentation. So thank you for being here, and now we will turn the time over to Shubh.
Okay. Thank you for the introduction. Hi, I'm Shubh, and I'm a PhD student in the Navigation and Autonomous Systems Lab at Stanford, advised by Professor Grace Gao. And today I'll be talking about our work on data-driven protection levels for camera and 3D map-based safe urban localization. Okay, so let us start by talking about urban localization using visual measurements. Urban environments house a variety of visual information that can aid in localization. For example, just by looking at this camera image, we can identify various structures such as buildings, trees, and road that inform us about our location and viewpoint within the environment. So the environment features captured by visual measurements, such as camera images, are useful in urban localization. And to identify and localize using these features, we require methods that can effectively process these complex visual measurements. And one such category of methods is data-driven methods. Over the last decade, data-driven methods have emerged as a powerful way of working with complex and high-dimensional visual measurements for the purpose of localization. And these methods commonly employ deep neural networks, or DNNs, which have several useful features. For example, DNNs can capture 3D structure information from 2D camera images. And this is a difficult task in general because it requires knowledge about the various objects that are present in the environment and how they appear on 2D images. Also, they can model complex relationships between different kinds of inputs, such as camera images and 3D maps of the environment. And this is very useful for localization because it also requires comparing information across different sources of inputs. And one more feature I would like to mention here is that DNNs can also model uncertainty in their outputs up to some extent as a function of the inputs. And this means that DNNs can provide a measure of confidence that is associated with the output and not just the output value itself. So all of these features make DNNs quite useful for localization within environments using visual measurements. However, DNNs also have certain limitations. For example, the data that is used for training a DNN is assumed to be similar to the data that a DNN encounters during evaluation. And this assumption does not hold in practice because real-world data can be very diverse. And so the similarity cannot be guaranteed. And because we cannot pin down the exact way that a DNN learns from the data to estimate the output, correct operation of a large DNN cannot be verified for all inputs. And this is very important because prior research has shown that DNNs can also be very fragile. For example, changing the inputs to a DNN by a small amount can produce widely different outputs and sometimes even incorrect ones. And while DNNs can model uncertainty to provide a degree of confidence in their outputs, it has been shown that this uncertainty can be overconfident since it is in the end learned from the training data itself. So all of these limitations make it difficult to employ DNNs in situations where the focus is on ensuring safety associated with localization. And this is the motivation for this work, since as we know, ensuring safety or integrity in localization is important for any real-world navigation system. And one such important measure of localization safety is protection level, which we tackle in this work, which provides a statistical bound on the magnitude of position error that is between the true state and the erroneous state that is given to us. And for road applications, this bound is calculated along the lateral, longitudinal, and vertical directions, such that the probability of the actual position error exceeding this bound is within a specified integrity risk. So this is the main problem that we address in this work, which is to estimate protection levels from visual measurements using DNNs. And to compute these protection levels, we need to estimate the position error that is between the unknown true state and the known erroneous state, and characterize the associated uncertainty as well. To our knowledge, this is the first such effort towards calculating protection levels from visual measurements using DNNs. So here is the outline for the rest of this talk. I would next talk about how position error can be estimated using visual measurements such as camera images and 3D map, which are the measurements that we consider in this work. Then I'll talk about how uncertainty in DNNs is typically characterized. Then I'll move on to our main idea for estimating the epistemic uncertainty, which is one of these types of uncertainty in DNNs. And then I'll talk about with more details about our approach, followed by experimental validation and conclusion. So first about position error. Since protection level is a bound on the position error, we need a way to assess this position error using visual measurements at any given erroneous state that is within the environment. And for the purpose of this work, we assume that the erroneous state is available to us either through prior knowledge or through a separate imperfect localization algorithm. And it roughly lies in the vicinity of this unknown true state. To get to the position error, we utilize two main sources of information. The first is a 3D map of the environment that contains information about the various structures that are present within the environment and their locations. The second is a camera image that is captured on board the navigating vehicle and contains information about how the environment looks like around the actual position of the vehicle. So we use these particular sources in this work since cameras are inexpensive as compared to other visual sensors such as LiDAR, while they're able to capture rich visual information about the environment. And 3D maps are captured and stored separately, so both of these sources together do not add a significant cost overhead for our task. To estimate the position error from these sources, many approaches have been proposed in recent literature, which mostly use different types of these maps. A common framework in these approaches is to first construct a local view that is in the reference frame of the erroneous state from the map, and then match it with the camera image using a DNN. What kind of local view is used for this matching depends on what kind of 3D map is being used, and that impacts the precision of the position error that is estimated from the matching process. So we need to consider what kind of 3D map should we be using in our approach for calculating the protection levels. And many different types of these 3D maps exist that are publicly available. And these are collected and maintained by various organizations and databases, such as USGS, Open Topography, and 3D City DB. Some examples of these maps are the LiDAR maps that are or point clouds that are constructed by stitching together several measurements that are collected from a LiDAR sensor. Or another type is polygon meshes, which are further filtered and refined version of these maps that also contain information about the shapes and structures of different buildings and roads in the environment. And even more variants exist, but among all of these, LiDAR maps are easily available and contain precise structural information about the environment. And so we use LiDAR maps in this work. So the second requirement of computing protection levels is to characterize the uncertainty that is associated with the position error. And that is computed using a DNN. So we need to characterize DNN uncertainties. And the DNN uncertainty is typically categorized in two types. The first type is called the Alliatoric uncertainty, which is defined as the variability in the output that comes from the noise that is inherent in the inputs. And what this means is that Alliatoric uncertainty captures the precision that can be achieved in the outputs based on whatever types of inputs are available. Some example sources of Alliatoric uncertainty are a lack of identifiable structural information that is present in the map. For example, an open field that does not have many structures to help with localization you would expect to get bad position errors estimated from that. Other sources could be lighting variations in images, such as glares, or even sparsity that is present in LiDAR maps. A good thing about Alliatoric uncertainty is that since it is reflected in the data that is used for training the DNN, can also be estimated by the DNN itself. For example, the figure on the right shows regions that have high and low Alliatoric uncertainty, and both of these are reflected in the data. The second type of uncertainty is called the epistemic uncertainty, and it arises from a lack of knowledge about the best model that is available for a task. And some example sources of epistemic uncertainty are differences present between the training and evaluation data. For example, uncertainty that arises when a novel input is used that is not seen during training for evaluating the DNN. And other sources for this type of uncertainty are presence of inadequate details about the environment structure in the inputs, such as due to memory limitations, or even approximation errors in the DNN. This uncertainty is a bit more challenging to work with because it cannot be directly estimated by the DNN. For example, in the figure on right, we can see that the region with high epistemic uncertainty is the one for which training data is not available. And so we cannot expect a DNN to have a good estimate of this uncertainty. And there has been some prior work in estimating these types of uncertainties for DNNs. And I have highlighted some relevant approaches here. One method for estimating uncertainty uses ensembles of DNNs that are trained for a particular task, and where each DNN within the ensemble is slightly different from the others. The overall variance in the outputs from these DNNs within the ensemble gives us the overall uncertainty that is associated with the task. And these ensembles have been created in different ways in literature, for example, by starting the training process with different initializations, or by constructing these DNNs by storing them at different times within the training process of the same DNN. And another work that I have highlighted here looks at characterizing the overall uncertainty associated with a task by combining estimates of Alliatoric and epistemic uncertainty, as we have discussed. The Alliatoric uncertainty in this work is modeled as variance in the output, and the epistemic uncertainty comes from an ensemble of DNNs, all of which have randomized connections. This can also be seen in the figure on right, which is the top figure, where both of these uncertainties are categorized for a particular image. And it can be seen that both these types of uncertainties contribute to different portions in the image, so they are characteristically different. And one last approach that I have mentioned here is called test time data augmentation, which considers outputs of the DNN for different random augmentations of the input to characterize uncertainty. For example, in the bottom figure on right, we can see the random augmentations of the image of an eye, which are used as inputs for characterizing uncertainty. While all of these approaches estimate the uncertainty in DNN outputs, the estimate itself depends on the training data, either for learning the components in the ensembles of DNNs, or for learning the invariance process for the input augmentations. Furthermore, these approaches are not designed specifically for the task of estimating position error and eventually protection levels, which is the focus of our work. So here is our main idea for estimating the epistemic uncertainty. So we start by considering a DNN that has two inputs. One is the camera image that we have available, and the other is a local view of the map. This local view is in the reference frame of an erroneous state that is given to us, as can be seen in the figure on right. Using the DNN, which takes both of these as inputs, it estimates the position error that exists between the erroneous state and the unknown true state. And so what we want to do is characterize the uncertainty that exists in this position error output. And to do that, we start by constructing a perturbation of this erroneous state to construct a different candidate state that has its own associated local view. We then use this new local view along with the camera image to evaluate our DNN and get a different position error output, which is now this time associated with the candidate state and is between the candidate state and the true state. Because this erroneous state position error, which was estimated earlier, the perturbation and the candidate state position error are all geometrically related, we can project one error onto the other using simple geometric transformations. And once we can do that, we can compare these values that we get to get the uncertainty. And that is the crux of this idea. So we can repeat this particular process for different candidate states and characterize the overall uncertainty associated with position error. This process can further be generalized to consider both position and rotation errors between the estimated state and the true state. So this is the key message of this slide, that we estimate the epistemic uncertainty by comparing position error that we get for different candidate states. So here are the three main key aspects of our approach. First is that we estimate the position and rotation error using a DNN, where the inputs to the DNN are a camera image, 3D LiDAR map, and an estimated state that comprises of a 3D position and an orientation. The output of the DNN is a position and a rotation error here. We characterize the uncertainty in two parts. The first is Alliatoric uncertainty, that is modeled as a position error covariance using DNN. And the second is epistemic uncertainty, that is determined explicitly by evaluating the DNN output at different perturbed candidate states, as we just saw. And the third aspect is that we estimate lateral, longitudinal, and vertical protection levels using this characterized uncertainty, which is the main objective. So here is a high-level framework, which is, so we start by considering an erroneous state that is given to us under 3D LiDAR map, and we select different candidate states that are near this erroneous state. And for each of these candidate states, we project the depth from the 3D LiDAR map to construct these different local views, each of which is associated with a different candidate state. We then use these local views along with the camera image that we also have available as inputs to the DNN to estimate a position error vector and a rotation, as well as a measure of Alliatoric uncertainty, which is the position error covariance. And this process is repeated for all the different views that we have constructed in the previous part. Then we characterize the epistemic uncertainty from all these different evaluations for candidate state by projecting the resulting values to the erroneous state reference frame and propagating the uncertainty along each of the lateral, longitudinal, and vertical directions. We also have a provision to handle DNN failures or possible DNN failures in our process. And for that, we compute outlier weights and use them to construct an error probability distribution. And finally, we get protection levels from this constructed error probability distribution. So first, we will start by talking about the process of constructing local views and evaluating the DNN for position error and Alliatoric uncertainty. So our approach for estimating position error using DNN is based on a previous work called CMRNet, which uses the DNN to estimate the relative position and rotation starting from an initial state. Similar to CMRNet, we use a 3D LiDAR point cloud as our environment map. And the local view for this particular 3D map is constructed by projecting depth from this map to the camera frame, so the image frame of reference itself. And this process of constructing local view happens in 3 steps. Starting from a given state in the map and a 3D LiDAR map, we rotate and translate the map to the reference frame of the state. And then we project rays from the camera center and identify the points that are not occluded. We then project these non-occluded points to the frame of reference of the camera and finally obtain the local view, which is an image of the depth as seen from the state. Next, we want to use this local view for getting our position and rotation error. And for this, we use an architecture that is based on the CMRNet architecture itself. So the inputs to this architecture are the local view and a camera image that we use, and it outputs a 6 degree of freedom error, which comprises of the position error and the rotation error. And these position and rotation errors can also be visualized in the figure on bottom. We train this network using 2 different loss functions. The first of which is Huber loss, which penalizes position error that does not match the ground truth, while reducing the penalty for outliers. The second loss is the quaternion distance loss that penalizes the rotation error output. The second part of our DNN is the covariance net, which estimates the Alliatoric uncertainty using the same inputs. And the uncertainty is estimated in the form of a covariance matrix, which is parametrized by diagonal standard deviation parameters and off-diagonal correlation parameters. This parametrization is motivated by a previous work on modeling DNN uncertainty. We train this covariance net using a third loss function, which is the Gaussian log likelihood loss, and it penalizes both the covariance and the position error that was estimated from the CMR net based on ground truth. So now that we have talked about getting the position error vectors, rotation error vectors, and the position error covariance, I'll now talk about characterizing the epistemic uncertainty. And we start by considering the estimated position and rotation error from a single DNN evaluation for the erroneous state. We use these obtained values to project the errors along the lateral, longitudinal, and vertical directions to get 3 error values, 1 for each direction. We then repeat this process for the different selected candidate states, where we convert the DNN evaluated position error and rotation errors for these states to the reference frame of the erroneous state itself. And before projecting them, this is done before projecting them along the individual directions. This way, we can get the different error values in each direction that together characterize the epistemic uncertainty. Since we want to get the overall uncertainty that combines both the epistemic and Alliatoric, we now have to propagate the Alliatoric uncertainty that we have estimated from the DNN for each candidate state. Since each of the error conversions that happened before is a linear transformation, we can propagate the covariance matrix for Alliatoric uncertainty through these linear transformations. And using the final propagated covariance matrix, we can get the Alliatoric uncertainty in each of the directions from the diagonal terms of this matrix, as can be seen in the figure on right. Now, apart from propagating the covariance matrix that captures the position error uncertainty in DNN, we also want to account for the uncertainty in estimating the rotation errors from the DNN. And to do this, we assume small errors in rotation estimation by the DNN. And for this assumption, we can derive an analytic approximation of the increased uncertainty along each of the directions. And the term for that can be seen in the middle. And this term depends on the rotation and translation errors that are estimated from the DNN. And there is also a third term, which is highlighted in blue, which is the expected rotation error. And this term is pre-computed by evaluating the trained DNN's performance on the training and the validation data. A nice thing about this expression is that the expected rotation term only needs to be computed once and can be reused for the different rotation and translation outputs from the DNN for estimating the overall uncertainty. So now that we have talked about characterizing the types of uncertainty and getting the different position errors, we now move on to computing outlier weights. So why do we need to compute outlier weights? The reason is that we want to handle situations where the DNN can fail to provide a reasonable output for certain kinds of inputs. And this can happen, for example, when there is a low overlap between the camera image that we have and the local view from the map that we construct. And which is indeed probable because we select different candidate states in the vicinity of the erroneous state. And it is not guaranteed that the local view would always contain features that are in the camera image. So to compute the outlier weights, we use the mean absolute deviation metric and use an exponential weighting scheme to compute the weight values themselves. And once these weights are computed, what it looks like is something like the figure on the right, where small weights are assigned to possible outlier values. Using these different computed outlier weights and the uncertainties that we propagated in the previous stages, we then construct the overall error probability distribution in each direction. And this amounts to a Gaussian mixture model, since each of these individual uncertainties is a Gaussian, and which can be the expression for which can be seen in on the bottom right. And the weights for this Gaussian mixture model come from the outlier weights, and the mean and the covariance terms come from the propagated uncertainties. So now that we have the error probability distributions constructed for each of the directions, the last step is to actually get the protection levels. And visually, protection levels can be estimated as the point along the positioning error axis, beyond which the position error probability distribution integrates to the specified integrity risk value. Numerically, we estimate protection levels using the interval halving method for line search, where we take advantage of the fact that Gaussian mixture models have a simple analytic expression for their cumulative distribution function, which is based on the CDF of the normal distribution itself, which is the expression that can be seen on the bottom. And so we can very efficiently evaluate this to get the prediction levels. So next, I will move on to experimental validation and conclusion. For experimental validation, we use the Kitty visual odometry dataset that contains various urban driving scenes and RGB camera measurements. And it also contains the different ground truth positions and orientations that we can use for validating our protection levels. For the 3D environment map, we use LiDAR point cloud measurements, which are also available within the dataset, and combine them together using SLAM corrected ground truth, which is available from a prior publication. So here are the details about our considered training, testing, and validation datasets. For training, we use some sequences from the overall Kitty dataset, and we generate the erroneous state randomly within a 2-meter translation and a 10-degree orientation of the true state. For the candidate states, we use smaller translation and orientation intervals, which is 1 meter and 5 degree, and we select them about the erroneous state instead of the true state. Overall, for the training dataset, we have more than 10,000 camera image frames. The validation and test dataset uses a different sequence that is not seen during training, and the erroneous state and candidate states are generated similar to how it was done for the training dataset. And we use more than 4,000 camera image frames for the test dataset and 100 frames for the validation dataset. Here are some more details on the experiment parameters and considerations. For training our DNN, we use the ADAM optimizer, which is set to a learning rate of 1e-5. And we use a batch size of 24, which is also same as the number of candidate states that we use, which is 24. And we train this overall DNN on a single NVIDIA Tesla P40 GPU using a mean variance split strategy, which means that we alternate between the training of CMR net parameters and between the optimization of covariance net parameters. For all our experiments, we set the integrity risk to 0.01, which is what we use for verifying whether our generated protection levels can actually achieve this integrity risk. And we use alert limits that are based on suggested specifications for mid-sized vehicles based on a previous publication. And the values can be seen on the figure on right. To design metrics for quantitatively evaluating our protection levels, we use the Stanford diagram, which shows the relationship between position errors, protection levels, and the alert limit. It divides these relations into 3 main categories, which are shown here on the figure on right. And the most important region for safety here is the red region, which is called the hazardous misleading operations. And this region corresponds to the cases where the protection levels are smaller than the position error, and so the bound fails. But then there is the green region, which is the nominal operations. That is the region where the actual error or the position error is below the alert limit and below the protection level. So everything is working all right. The upper yellow regions are the part where protection level is larger than the alarm limit, and so the system is declared unavailable. Based on these 3 regions, we designed 3 metrics. The main metric that we used is failure rate, which is based on the red region, and so it is the most important metric. It measures the fraction of the total estimated protection levels that lie in this particular red region, and we want to ensure that this particular fraction is smaller than the integrity risk that we have specified, which is 0.01. The other metrics are false alarm rate and bound gap, which measure the tightness of the protection levels that are estimated by our approach as bounds on the position error. For instance, false alarm rate is the fraction of protection levels that lie in the bigger yellow region. And so we want lesser of those to be present there for a very tight bound. And the bound gap is the difference between protection level and the position error in the green region. And that also measures how tight the bound is. So here are some qualitative results for horizontal protection levels computed by our approach along a trajectory. So the horizontal protection levels include the lateral and the longitudinal directions. And all of these values are visualized at every 5th time interval for the purpose of clarity. The red boxes denote the protection levels, and it can be seen that they successfully enclose the position errors, which are present in state estimates or the erroneous states, which are shown as blue dots. And similar results can also be observed for the vertical protection levels computed by our approach, which are shown in red. So it can be seen that are successfully enclose the position errors, which are in blue, and all of this happens with a small bound gap. That is the difference between the blue and the red lines. Next, we have the performance evaluation for the protection levels computed in each direction, starting from lateral protection levels. The plot on the left shows the different protection levels estimated by our method for over 15,000 samples. And the corresponding regions in the Stanford diagram are highlighted in the figure to show that very few protection levels actually lie in the red region, which is the most important part for safety. This is also reflected in the table, where we have done an ablation study with protection levels computed using only Alliatoric uncertainty, both Alliatoric and epistemic uncertainty, and using Alliatoric, epistemic, and also outlier weighting schemes. So Alliatoric only protection levels have a higher failure rate than the desired integrity risk, which shows that the Alliatoric uncertainty itself is overconfident in its output. So while the failure rate associated with our other two approaches, which is Alliatoric and epistemic uncertainty, and on including outlier weights, both match the integrity risk value, which is 0.01. So while the metrics of the tightness of the bound, which are false alarm rate and the bound gap, they increase from Alliatoric uncertainty to Alliatoric plus epistemic, the increase itself is not that significant, and it further goes down when outlier weighting is incorporated, which shows that this particular bound can be made tighter without losing on the failure rate by incorporating good outlier weighting strategies. And we can observe similar performances for the longitudinal protection levels, where the red region, which is the hazardous misleading information region, contains much fewer protection level samples than the other regions. And the failure rate achieved by the Alliatoric plus epistemic and with outliers weighting matches the integrity risk that we have specified. And yet again, we can see similar results for the vertical protection levels. And specifically, we see that the performance of our approach for vertical direction is much better, owing to the capability of DNNs in better estimating the position error associated with the vertical direction. So the failure rate associated with this direction is much lower, and also the bound is much tighter, as can be seen by smaller values of false alarm rate and the bound gap. So in conclusion, we have developed a data-driven approach to compute protection levels from a camera image measurements and a 3D map of the environment. We have characterized epistemic and Alliatoric uncertainty that is associated with DNN-based outputs for computing protection levels. And we have validated our approach using real-world data and shown that our estimated protection levels exhibit a sub-meter bound gap and a failure rate that is contained within the integrity risk, which is 0.01. And with that, I would like to end this talk, and I'm open to any questions. Thank you.
Thank you so much. Great presentation. If you have questions, please submit them by clicking on the Q&A button in your viewer, and we'll address those one by one with our presenter. So we have one question. It says, how do you see the generalization of this approach beyond KITTI?
Oh, okay. That's a great question. Yeah. So that is true that one challenge here is that since most of our evaluations are so far restricted to the KT data set, it would be nice to see how this specific approach performs when we use various different kinds of environments. And that is something that we're trying to work towards, where we do a much more larger scale evaluation on the different types of environments that are available. One thing I would definitely say, though, is that because this approach kind of assumes that you're using the same vehicle for evaluation, the requirement is that the data set must be collected in similar situations, which is when the camera is mounted on the same spot on the vehicle in the same orientation, and so on. So that's the only restriction, but otherwise, I don't see a reason why it should not be able to generalize to different situations. Yeah.
Great. Thank you. We have a question here from Michael Baraducci, who asks, how much of a factor is differences in lighting and shadows and glare, day and nighttime for the position errors?
That's actually a great question. So we have actually observed quite a significant variation in terms of the position errors that we get for bad images, which is when a glare appears on the camera. But the good part is that it gets characterized as the Alliatoric uncertainty, which is the covariance output from the DNN, because during glare situations, the DNN is by itself, it knows that the output is not super certain because it cannot match the output with the ground truth in those situations. So that gives a much higher covariance output associated with it in those situations. So that is mostly characterized as the Alliatoric uncertainty part.
Okay, great. We have another question here. It says protection levels, protection levels bounding errors can be a safety critical function in some applications. In those cases, 1% may not be sufficient. Is this approach generalizable to safety critical protection levels, several orders of magnitude, smaller probabilities?
Yeah, thanks for that question. So far, since it's like still an early work towards this particular way of characterizing protection levels, we have not been able to achieve much for this similar level of accuracy for much smaller integrity risk values, purely because the bound itself does not remain as tight. So if we go for much smaller values than 0.01, the bound becomes much trivial because the Alliatoric uncertainty or the precision level that can be achieved from the DNN itself cannot match that level of performance. But ideally, if we can improve the performance of the DNN itself and the precision in it, we should be able to achieve much more tighter bounds for even smaller integrity risk values, which is what we're trying to go towards.
Okay, our next question says the input to the DNN is the image at the true state or candidate error state. If the latter, how is the position error estimated? That is DNN estimating the position and subtracting it from a known state?
Can you repeat the question again, please? I think I did not completely understand it. Actually, let me read it.
It's in the chat window if you want to take a
look. Then put the DNN image in the true state. Candidate. All right. Yeah. So the image is captured by the onboard vehicle. So the image is actually how the environment looks like from the true state. So if I go back to my original main idea figure, yeah. So the image is actually collected from the true states. So by looking at the erroneous state local view, the DNN has access to information of how it would expect the environment to look like if it was looking at it from the erroneous state. So now it has both of these pieces of information, and so it can get the relative transformation between these images, which is the position error is estimated.
Great. So if you had a lot more training data, would you expect any improvement or much improvement in your test results?
So far, I think what would improve is the estimate of how good of an Alliatoric uncertainty that we can get for certain inputs, as well as the precision of the DNN would improve somewhat. But I believe that would still not be sufficient enough to get to much smaller levels of integrity risk, such as maybe like 0.001. To do that, we would have to use some more higher fidelity approaches, which is like using a much more complex DNN that can specifically model parts of the image or see different parts of the images to characterize this position error. But I definitely expect the performance to improve somewhat by using more training data.
Okay, great. Well, thank you. That answers all of our questions we had today. Again, Shubha, we appreciate your time and your thorough preparation here. This has been fantastic. And also recognize Professor Gao. Thank you both for being willing to provide this webinar for us. So again, thank you both and have a great day.
Thank you.